Hi ladies and gentlemen, this is a brief video that looks at section 5.2 and talks about what we're expecting from the problems at the end. Let's take a look at what this says. So here in 5.2 we're talking about error associated with numerical differentiation. I touched on this briefly in class to let you know that the error associated with numerical differentiation is severe. But we want to understand exactly what our parameter space is for looking at data and trying to find rates of change. So the example that's in the textbook, which you should walk through, looks at the second derivative approximation. So in this case, it is the central difference. And then we look at the reality of the fact that anytime we use double precision arithmetic, we have round-off errors associated with representing numbers in the computer. We cannot represent square root of 2. We can only approximate. And we have errors that are on the range of 2 to the negative 52nd power because of the 52 bits in the mantissa. And so the derivation here just discusses the final result. So it goes through, and what we see is we have two forms of error associated with this. We have the numerical differentiation error. So we've taken the derivatives and we have this differentiation error. We also have error associated with floating point. And this is the double precision representation of the numbers in floating point. So what we want to do is we want to understand how these errors interact with one another. And what all of the homework problems are really doing is the same thing. They're looking at, given a function that's easy to differentiate, something where we can check our approximations against the reality of the values of the derivatives. And what we're going to do is look at the functions and their derivatives and then calculate the error associated with the derivatives, whether it's first derivative, second derivative, fourth derivative, whatever. And this gives you some indication. So let me give you an example that I've done. I've looked at the following function. So I've let f of x be equal to sine x. And then, of course, f prime of x is just cosine of x. And I'm comparing the actual cosine of x value at x equals 1. So I've picked a specific representation, x equals 1, against the first order approximation, which is the forward difference, f at x plus h minus f of x divided by h. And on a logarithmic scale, so I want to do this log because I want to take the steps back here logarithmically. I'm going to start at 10 to the 0, and then I'm going to take steps back all the way down to 10 to the minus 16. And what I expect to see is I expect to see the error getting better. Right, so over here we have error. And the reason, of course, it's log is I want a logarithmic scale for my error representation as well. So if I do this for the sine function, let me show you what the result looks like. I end up with this graphic. And this is the analysis that I want you to do. It's what I expect you to do for the homework problems in 5.2. Once you get this programmed up so that it will calculate the derivative at a specific value, as well as calculate the approximation to the derivative using whatever numerical method we're using, and calculate the error, which is the difference between the approximation and the real value, you'll be able to generate this plot. You notice that it's logarithmic down here on the horizontal axis and logarithmic here. So the first part of this is exactly what I expect, right? So as we decrease step size, so at 10 to the minus 4 step size, the error is a little bit less than 10 to the minus 4. And that's a direct result of what I'm doing here with my forward difference. The interesting part is this only continues to improve until about 10 to the minus 8. At 10 to the minus 8, the error reflects back up and starts to become worse. Unlike the right-hand side here, where I have literally a straight line, and what I want you to think about is what is the slope of that line, and what is the slope of that line telling us on a log-log plot. As mathematicians, this is the kind of thing that you have to be able to understand, and if you don't know it already, be able to do a quick lookup and figure out what the slope of a log-log plot is. The backside here is a little jittery, but it also has a generic slope associated with it here, and that's of interest to us, something for us to think about. Then what you're going to do as you continue on with the homework problems is you're going to use other methods. So this is an order H method. If I use a central difference, I'll have an order H squared. So what I've done is I've come up with a plot that shows both of these on the same set of axes. So in the red, I still have order H. And this is the plot that we were just looking at. In the purple, I have the central difference. Unsurprisingly, it's an order H squared method. So I am improving more quickly. Remember, we talked about this. If I have the step size, I expect a 1/4 reduction, or 1/4 the amount of error. And so the slope here is different. Again, understanding the slope of log-log plots is a useful idea. So we continue to improve until we get down to about 10 to the minus 5. And then we see the same behavior. It reflects and starts to take off along this slope. So one interesting thing is the fact that it has the same slope, or a very similar slope to what we saw with the order H method. And so we want to think a little bit about that. That's what it comes down to. The problems that you have are all of this exact same flavor. For you to take a look at the error associated with numerical differentiation and begin to understand how far can we push the step size before we start to actually have problems, and why do we have problems, and what is the impact of those problems. That's it. Good luck, and I'll see you in class.